Hey y'all, we're almost done with the summer session. I hope that you've been enjoying it so far. We're kind of on the downslope, meaning the easier part of the semester. There's much fewer formulas at this point, and just a couple more chapters to cover. And this chapter, chapter 13, is on non-parametric statistics. And the test I'll focus on in the lecture is called a chi-square test. So first, let me break down the difference between parametric and non-parametric tests. The tests that you've learned about so far in this course have all been parametric tests, even though I haven't used that term before. Those tests are called parametric. That means that they rely on an assumption that the data follow a particular distributional shape. And thinking of that particular distributional shape, we could take, for example, the normal distribution. And the normal distribution takes on a specific shape that's defined by a mean and standard deviation. We need to know what the mean of the shape is. That's a location value. So where does the shape fall in a number line? And how spread out is the shape? How fat or thin is the shape of the bell shape, right? So it's location and then it's spread. And those two values, the mean and the standard deviation, are called parameters. The parameters of the normal distribution are the mean and the standard deviation. Every distribution has parameters that define it or that give it its particular special shape. So we call tests that rely on distributional assumptions parametric tests. There are cases in research where it wouldn't be appropriate to assume that our data falls on a normal or otherwise distribution. And in those cases, we typically would defer to a test called a non-parametric test. And this is another whole umbrella of tests. Non-parametric tests are tests then that can be used, broadly speaking, when distributional assumptions are not met. And again, all the tests that we've learned about so far do assume that there's a distribution of means that follow a normal distribution or a t-distribution. This assumption can be violated under certain conditions. And the one that I'm going to talk about today is the case in which your variables are nominal. So if you're conducting a research study and you're interested in nominal or categorical variables, then they can't follow any sort of distribution, right? You don't have scores on a nominal variable that you could plot along a distribution. So inherently, these data cannot be handled or analyzed with a parametric test. Instead, we must use a non-parametric test. And the one that I'll talk about again today is called a chi-square test. This is not pronounced chai like your chai latte. It is chi like the sound in the word sky. And this is a test that's really useful for research about nominal variables. So just a little example, a little toy example that we'll work through today. Are people more likely to order hot coffee in wintertime and cold coffee in summertime? And I'll just pose the question to you, how could you conduct this study? You could think about it for a minute. Maybe you could pause the video. It's good practice to think about, if you're the researcher and you have this research question, what design would you use to collect this data? And then how could you analyze it? Well, let's say that I choose to observe 6 participants ordering their coffee at a single location in the wintertime and then again in the summertime. And I'd probably control for things like day of the week and time of the day. So I would want to make sure I'm going, if I went in the morning time in the winter, I would also go in the morning time in the summer. And if I went on a weekend day in the winter, I also want to make sure I go on a weekend when I go back in the summer to collect my data. So I have 6 observations from my winter trip and 6 observations from my summer trip. And remember, my research question is, are people who drink coffee in the winter more likely to order hot coffee? And are they more likely to order cold coffee when they're drinking coffee in the summertime? So I have my clipboard and I'm sitting in the coffee shop and I just keep track of what kind of coffee people are ordering, whether it's hot or cold. So I have a total of 12 observations here. 6 of them were collected in wintertime and 6 of them collected in summertime. Okay, so all the tests we've been learning about so far, the first thing you would do is calculate a mean. How could I calculate a mean for these data? They're nominal data. So right off the bat, I'm stuck. Means won't work for nominal variables, but what will work, and in fact what we'll use to our advantage, are counts or frequencies. And the concept of the chi-square test will use counts and we'll compare the expected counts with observed counts in each category. So we have categories for both of our variables, and we're going to come up with what we would expect to see based on a null hypothesis. And then we're going to look at our data to see if what we actually saw is different from what we would expect to see under a null hypothesis. And to do this, we're going to set up what we call a contingency table. And that looks similar to what you have in front of you on the screen. Specifically, this is a 2 by 2 contingency table. That's because both of my variables have 2 levels. So 2 levels for the season and 2 levels for the coffee order. So this is a 2 by 2 contingency table. The first thing that I want to do is calculate the expected counts. So if the null hypothesis were true, or if people were just as likely to order hot or cold coffee in the winter as in the summer, that there's no effect of season on coffee orders, then we would just expect that each cell would have equal values, right? So in winter, people would order hot and cold coffee equally. In summer, people would order hot and cold coffee equally. Or you could think about it as, for hot coffees, people are equally likely to order hot coffees in the winter as they are in summer, and people are equally likely to order cold coffees in winter as they are in summer. So if there's nothing going on here, if there is no relationship between season and coffee orders, then we would expect to see 3 hot coffees ordered in winter, 3 hot coffees ordered in summer, 3 cold coffees ordered in winter, and 3 cold coffees ordered in the summer. And there is a little formula that you can use to calculate the expected values for each cell of a contingency table. And that is shown here on the screen. E equals R over N times C, where R is the number of total people for the row, C is the number of total people for the column, and N is the overall total sample size. So just looking at, and this will be the same for any one of the cells in this particular contingency table, but if we look at this first cell, hot coffees ordered in winter. First, I take R, the number of people in this whole row, so that's the whole hot row. There are 6 observations here. 3 in winter and 3 in summer. So I have 6 divided by the total number of observations, which is 12, right? 3 times 4 different cells is 12. So 6 divided by 12, and then times the number of observations in the column. So the column that I'm working with is the winter column. And you can see that there are 6 observations in wintertime. 3 that ordered hot coffee, 3 that ordered cold coffee. So for the expected count in that column, I get 6 divided by 12 times 6 equals 3. So now that I know my expected counts under the null hypothesis, I want to take a look at my observed counts for each cell. So I just look at my raw data table and gather the information I need for my contingency table. So how many people ordered hot coffee in the winter? That looks like 5 people ordered hot coffee in the winter. So that means that 5 is my observed count for this cell. And you could pause the video here and try to recreate the observed values for each of the other cells of the contingency table. And hopefully you got these values. 2 people ordered hot coffee in the summer, 1 person ordered cold coffee in the winter, and 4 people ordered cold coffee in the summertime. So just looking at these counts, you can see that the observed counts are different than the expected counts. And you can see that it does appear that people more often ordered hot coffee in the winter and cold coffee in the summer. But let's calculate a statistic, right? We are in a statistics course. We will calculate a statistic that will allow us to see if this is significant, if this effect is significant, or if we're able to reject the null hypothesis. So we will use these observed and expected counts, O and E, to calculate a chi-square value. So chi is a Greek symbol that looks kind of like a fancy X. So the statistic is chi squared. And we calculate it as the sum of this whole thing here. The sum of observed minus expected squared over expected for each cell. So this sum means sum over all the cells. So I do this part for each cell and then add up the values to get our chi-square statistic. And then, unsurprisingly at this point, I will look up that chi-square value in a chi-square table and compare it to a critical value. And the critical value that I'll find in the table will be based on degrees of freedom that's equal to number of rows minus 1 in my contingency table times number of columns minus 1. So remember, our contingency table for our study is a 2x2 table. It has 2 rows and 2 columns. So my degrees of freedom here is 2 minus 1 times 2 minus 1. In other words, we have 1 times 1 gives us degrees of freedom of 1 for this test. Okay, so I have the contingency table on this screen with our observed and expected counts on the left-hand side. So you could try to give this a shot on your own now if you pause the video. I'll walk you through the first cell here, hot coffees in the wintertime. We thought that 3 people would order coffee if the null hypothesis were true, but 5 people actually ordered hot coffee in the winter. Okay, so let's plug those values in. We get 5 minus 3 squared over 3, okay, equals 2 squared over 3 equals 4 over 3. So if you do that for each cell, you should get the values that I see here on the screen. And then remember, for the chi-square statistic, we add up all these values, right? So I have 1.33 plus 0.33 plus 1.33 plus 0.33, and I get a sum of 3.3332. And that is my chi-square value. So my chi-square value with degrees of freedom 1 equals 3.3332. Now I go into my chi-square table. Let's do the test at the 0.05 level and use degrees of freedom 1 because I had a 2x2 contingency table. and I find my critical cutoff score for this test is 3.841. Okay, and you can see that the chi-square distribution, a little bit like the t distribution, changes in shape with degrees of freedom. So you can see that the chi-square distribution with degrees of freedom equal to 1 looks like this. It's a funny looking distribution. But the critical cutoff value here equals 3.841. So anything beyond that we would reject, but it looks like my value is here, 3.33. So that does not fall in the critical rejection region, so I conclude that I cannot reject my null hypothesis. In other words, I don't have evidence to say that, or to support the hypothesis that people order more hot coffee in the winter and more cold coffee in the summer. But remember that statistical significance is not always the same thing as real-world significance. So you've learned about effect sizes for other tests in this course. We could also calculate an effect size for the chi-square test. And this is measured by what we call the phi coefficient. So Kramer's phi is equal to the square root of your chi-square value divided by n over degrees of freedom that's your smaller, either rows or columns, degrees of freedom. So in this case, we have the square root of 3.33 divided by 12 times 1. And if you do that math, you get an effect size of 0.52. And if we had a significant finding, we might report this value alongside it to give some idea of how practically meaningful our finding is. Here are just some of Cohen's suggestions for what a small, medium, and large effect size is. So with degrees of freedom for the smaller one of the rows or columns equal to 1, then the cutoff values are 0.1 for a small effect, 0.3 for a medium effect, 0.5 for a large effect. So our effect would be a large effect. And this is how we could report our findings for a research study. The test statistic was not significantly different from 0. P is greater than 0.05 because the probability of getting this value was not less than 0.05. Remember, because our value did not fall in that 0.05 rejection region. Thus, we don't have evidence to support the hypothesis that coffee selection depends on the season. Just one final note about chi-square tests. The example that I walked through in this lecture is called a chi-square test of independence because there are multiple variables and we're testing whether those two variables are related to one another or whether they're not related, or in other words, whether they're independent or dependent. This is a very common use of a chi-square test, but there's even a simpler version. You could use a test called the chi-square goodness of fit test. And that test would just tell us whether on one variable, the counts are equal or different across levels. So we could ask, do people order hot coffee or cold coffee more often? So notice there's only one variable here, and it's the temperature of the coffee. And I just want to know if the frequencies of hot coffee are higher or lower or the same as the frequencies of cold coffee. And I could use a chi-square goodness of fit test to test that hypothesis. That's the end of this lecture on chi-square tests, a pretty common non-parametric approach to handling nominal data. And again, as always, let me know if you have any questions or post them to the discussion forum on Canvas.